Hello everyone and welcome back to the next session on duality theory. Now so far what we have seen in duality theory is how a linear programming problem, which is actually in the standard primal form, can be converted into its duplicate version, what we call it as dual form. So every LPP will have two forms. One is the primal form and the other one is dual form, and you know the methodology how to convert the original LP problem into its duality. Now in this particular video, we are going to have a look at dual simplex algorithm. That means the algorithm which is required to solve the linear programming problem in its duality fashion, right? So the steps are given in front of you. Just have a look at it. Of course, we'll try to understand this algorithm with the help of example. The more and more problems you solve, the more and more grip you'll have on the algorithm. Now closely observe step 4, right, which is test the nature of delta J in the starting table. Now this is the difference in terms of drawing the conclusion whether the obtained solution is optimal or not. Okay, so we will see how this particular step 4 plays a vital role in problems of nature where we use dual simplex method or dual simplex algorithm to solve linear programming problems. These are the remaining three steps. So let us straight away jump into the problem. Now we have a problem. This is how the problem will also appear for you. Use dual simplex method to solve the following LPP. So the objective function is of minimization type and you are given two constraints which are of greater than or equal to type. Okay. Now let us see how to solve this particular LPP using dual simplex method. Now, first and the foremost thing is you have to write this particular problem, or you have to ensure that this particular problem is in standard primal form, right? And you know what is standard primal form. So this minimization will get converted into maximization by converting the entire objective function, actually by multiplying with -1. And this greater or equal to constraint will be made as less than or equal to by multiplying the entire inequality constraint by -1. So the original LPP in its standard primal form comes out to be like this. So I have maximized z equal to, and subject to, look at these constraints, I have less than or equal to in all the cases. Okay, so the first step is over. I have converted the original LPP into standard primal form. Now let us see the next step. Now next step is, as usual, you are going to introduce slack variables because the constraints are less than or equal to. So since there are two inequality constraints, I am going to introduce two slack variables. Of course, I am not telling anything new. You have already done this in earlier LPP problems. So after introducing two slack variables, this is how my objective function looks like, and this is how my constraints look like, which of course after introducing slack variables, it has been converted into equality constraints. Right now, based on this particular LP model, I'm going to prepare my simplex table, and my simplex table looks like this. So again, nothing new. This is what you have done. Right now, my Cj is -5, -6 because they are the coefficients of the objective function, but my delta j now becomes 5, 6 and 0, 0. Okay, now go back to the earlier LP version where we said that if delta j is greater or equal to 0, the solution under test is optimal. Right now, here in the first step itself, delta j is greater or equal to 0. But since we are implementing the concept of dual method, we cannot draw conclusion that since delta j is greater or equal to 0, solution under test is optimal. Right now, that is what I want you to focus on, that step 4 of your algorithm. Look at this. This is the step 4. Right now, what step 4 says? Point 2 of step number 4. Let me take back you to the algorithm. Look at this. if all delta j are non-negative and at least one basic variable is negative, then go to step 5, right? Understand, right? So it is not an optimal solution. Let us look at it. If all delta j are non-negative, let me look at delta j. I have 5, 6, 0, 0. So the entire delta j is non-negative, and so it's an AND operator. At least one basic variable xb is negative. So look at the basic variable column. This is our basic variable column, which has got -2 and -4. So this condition is also satisfied. Which one? At least one basic variable is negative. So this is also satisfied and this is also satisfied, and hence solution is not optimal. Please understand. This is how you draw conclusion that solution is not optimal in case of dual simplex method. Okay. Now, after we draw conclusion that solution is not optimal, we make an attempt to find out the outgoing vector and incoming vector. If you recollect, in our earlier case, we used to have one more column on the right hand side which was giving us minimum ratio, right? And it was delta j and minimum ratio which was helping us to identify the incoming vector and outgoing vector. Of course, with what is that, pivot element and all such type of operations. But in dual simplex method, we are not going to have something called as minimum ratio, and hence minimum ratio absence will not help us to solve, the minimum ratio presence will not help us to solve the dual simplex method. So what do we do? Once we draw conclusion that solution under test is not optimal, we directly go to step 5. And what we do in step 5 of the algorithm is we find out the most negative value of xb. What is most negative value of xb? This one, -4, right? -4 is the most negative value of xb, which corresponds to basic variable s2. And hence we draw conclusion that s2 becomes the outgoing vector. Okay, s2 becomes the outgoing vector. Okay, then what happens is, to find the incoming vector, we compute the ratio between zj minus cj row and the key row, and we draw conclusion that entering variable is the one having maximum ratio, right? Entering variable is the one which is having maximum ratio. Unlike we had a minimum ratio in the earlier case, we have something called as maximum ratio in this particular case, right? Now, how is it calculated? It is calculated like this. Since S2 is the outgoing vector, we are going to calculate the incoming vector based on this ratio of delta j and this particular row. Means what? For x1 variable, right, the ratio is delta j divided by this column, this particular cell, because this for row S2 and for this particular column, this is the intersection cell, and hence we say 5 divided by -4. Similarly, for x2, it will be 6 divided by -1. And hence what happens? I will get the incoming vector like this. Max of 5 by -4 and 6 by -1, which is -1.25, right? Now -1.25 belongs to x1, and hence we draw conclusion that x1 is the incoming vector. So after this simplex table is drawn and we draw conclusion that solution under test is not optimal, we find the outgoing vector based on the value of xb, and we find the incoming vector based on the maximum ratio, and then draw conclusion that variable x1 comes in place of s2. I repeat, variable x1 comes in place of variable s2, and hence, okay, once we draw that conclusion, we make the pivot element as 1 and all other elements in that column as 0. I don't think I need to tell you this because we have done these type of operations earlier. And once I implement these two operations, I'll get my new simplex table like this. Okay, so this is my new simplex table, and you see x1 comes in place of s2, right? Now, let us see whether this particular solution is optimal or not. delta j is greater or equal to 0 is true, and one of the value of xb should be negative. So minus 1 and 1. So this is negative, and hence we say this particular solution is also not optimal. So we proceed for optimality. What we do? We implement the same step, and then we draw conclusion that the most negative value of xb, that is s1, is going to be the outgoing vector. And similarly, we calculate the incoming vector with this particular formula, right? And then the maximum ratio is minus 5, and hence we draw conclusion that s2 is incoming vector. So s2 comes in place of s1, right? S2 comes in place of s1, and we perform these row operations. And once we perform this row operation, we prepare the simplex table, which looks like this. Right? Now in this particular simplex table, we have delta j greater or equal to 0, and we do not have any xb with negative, right? And hence, since delta j is greater or equal to 0 and this is not negative, we draw conclusion that solution under test is optimal, and the optimal value is this one, right? X1 is equal to 2 and x2 is equal to 0. So I have this x1 and I have this 2, and hence x2 is x1 is 2, and since your original decision variable x2 has not gone in the simplex table, we say value of x2 is 0, and substituting these values of x1 and x2, we get maximum z is equal to minus 10, because we have converted that into standard primal form. But your original LPP is of minimization, and hence you draw conclusion that this value of the objective function is 10, right? So maximize z is minus 10, and hence minimize z will be 10. Just change the sign from maximization, so you will get the value of objective function for minimization. Okay, so this is how basically a dual simplex algorithm is used to solve any LP problem. Let me also go ahead with one more problem, and then I can give you one problem to solve on your own. Now this is the problem. Use dual simplex method to solve the following LPP, right? So I have minimization with the 3 decision variables, and I have 3 constraints. So the first step is I'll convert this into standard primal form, and when I do that, this is what I get: maximize, and all the inequality constraints have been converted into less than or equal to. Since there are 3 inequality constraints, I have added 3 slack variables, right? And then those slack variables are put into the constraints to convert the inequality constraints into equations, and then I prepare the simplex table. Okay, so once I prepare the simplex table, right, I'll just give you a hint, and I'll leave up to the reader to solve the problem, right? In the first simplex table, the basic variables are the slack variables, that is s1, s2, s3, and then you find out the outgoing vector and incoming vector based on the algorithm. And once we find the outgoing and incoming vector, at the end of the first step or the first simplex table, we draw conclusion that s1 is the outgoing vector and x2 is the incoming vector. So the variables x2, s2, s3 will form the second simplex table, right? And then the solution becomes optimal, and the optimal solution is maximum z is minus 4 by 3, and since the problem is of minimization type, the minimum z will be 4 by 3. Let me give you one more problem for your reference. So that is how basically you land up solving the LP problem using dual simplex method.